What the hey, we're recording. Because what are some things in biology you can think that grow exponentially or decay? Bacteria.
Growth rate.
Anything. Growth rate, population, things. So in other words, that's why exponential functions, and then of course, hopefully you remember the inverse of exponentials or logs. That's why exponentials and logs are used a lot in this class. Okay, so if you kind of hated them, when we get to things, when we do some calculations with them, because there will be that, once again, if you have a variable in the exponents, how do you solve it with logarithms? If you're like, yeah, I kind of remember that, we will go over that again, okay? So certainly you can see here that this is something very good at such as a population, meaning, you know, these people got to get out of my town because the morning traffic is getting bad, so we need to send some of y'all away. Well, not y'all, because y'all are paying for my, yeah, okay, all right. All right, so as I want to call you Rafiki, said the growth of the growth of bacteria, of course, and we also have to think of decay, so it can be an exponential decay, and then as I mentioned before, why most of you are taking this class, you need to know before you go and take your job interview when the drugs will be out of your system, correct? Okay. All right, so what we're going to do is we're going to look at the formulas for all of these. This is going to be one of these, and this might be something with notes that I'm just going to tell you what these are. Now, some of these, especially these last two, we're going to need, as some of you might remember in high school, the chain rule. Okay, so I'm just going to tell you, here it is. A couple of them we're going to look at, meaning by putting in values of h. But some of them, it's just, there it is, use it because I say use it, until we get to the chain rule stuff. So, if I want to find the derivative of f of x equals e to the x, okay? Once again, and so if I have this, f prime of 1, remembering that this means I'm looking at this function where x equals 1, I want to know how that function is changing. That's what that means, find the derivative at 1, okay? So, the only way I know how to do this, if I don't know and it's kind of a punchline, right, for those of you that already know this, I don't know what this derivative is, so what I'm going to go through my wonderful formula that we've learned to grow in love, that we're throwing away, right, because we're going to do shortcuts, but I'm going to prove this with this formula. So this is chapter 2 stuff. You can celebrate. You won't use this anymore, okay? And luckily, your guys' final, they don't make it, this class is dictated, what I have to teach. Your final's not even comprehensive. So if you survived this, you got it made in this class, okay? This is probably the hardest part of this class.
There's a final? We got it.
Okay, test number 3. All right, so you fail. All right, so I'm plugging in my x here, and I say for various values of h. Most of you that have a little bit of logic would say, well, why'd you pick 0.1? Why didn't you pick something smaller? Because I wanted to. That's what I felt like picking. Got a problem with it? Yeah. You keep going. I plugged this in, meaning my e to the 1 plus 0.1 minus e to the 1 all over 0.1. So that's my h, and I get this value. Say, well, Mr. McKee, oh no, let's just call him Soccer Dude. Mr. Soccer Dude says, well, I don't like that. Let's pick something smaller. So let's pick something smaller, meaning I plug this into my calculator. I get this value. I say, well, let's even go smaller because remember what a limit is as this is going to 0, meaning it's getting smaller and smaller and smaller. And let's go even smaller. Does anybody recognize this number?
E.
E. Say it with feeling. What I always tell the joke in, I don't even remember it now. Never mind. It was funny though. All right, so in other words, you have like the number pi, which is a number you've dealt with it probably a lot more. There also is this number e. This is a little history lesson over here. This is pronounced Euler, like the Houston Oilers. In other words, this was named after this dude. And of course is used, if you remember, in the natural logarithms, that's the base, okay? So that's all this information is telling you. But if you continue to do this, you will get closer and closer to this value. An interesting side note is where this really came from is this shows up with compound interest, which is, I find interesting because it started out with banking and just showing you that your bank account can grow exponentially if you are, putting money into it, a savings account, or your credit card can grow, so today's lesson, boys and girls, don't get credit cards. Interest. Yes. So, well, now I'm going to actually use the definition. The definition says I don't want to find the value at x equals 1. What I just found is the derivative for x equals 1. What I want to do now is through my entire definition for any x. And that's how you prove these. Okay, that's what we're doing. If you're sitting there staring, what is she doing? We're proving what this is. As Justin says, he already knows the answer is E. And so in this case, I plug in these values. This is probably something most of you hopefully remember. When you have the same bases, you add the exponents. So I kind of did it backwards. I split those up. And now I can see I can factor the x. So I factor that out. I have this piece left. Remember that the limit... Remember that I'm going to so fail you, and I'm going to enjoy having you for 5 years in a row. All right. So remember the limit, the only thing the limit cares about is things with an h attached to it. It could care less about that. That's a constant. So I actually out front, and so and eventually I can pull it out front here. All I care about that h is going to 0 is this piece right here. Can't let that go to 0 because, right? All right, so I don't know how to find that limit, meaning that all I know how to do is just to plug in, and notice I'm only interested in this piece, is to plug in some very small values here. So as I'm plugging in really, really, really small values of h from the left, from the right, limiting value for this piece is actually going to 1. Okay, so that piece is going to 1. So I write this all out, back my limit again. Once again, I separate these into two limits. Remember we said we can do that. This is a product of a limit is the same as a limit of, or a product of two limits. This piece right here is a constant. It's just a number, e to the, you're going to plug in whatever x it is. And so I bring that out front and I get this piece from up here equaled 1. This is by far, I put you a little cartoon. This is by far the student's favorite derivative. The derivative of e to the x is e to the x. And it's like, really?
That's amazing.
It is. It's, it took us, 21 slides to do that. All right, so this is definitely one you want to remember because it's a question.
Yeah.
Oh, yeah. So down here, remember, if you have constants, we can pull front, meaning I'm doing this. And you can only do this if you're multiplying. I see students try to do this if that was like 2 plus, and you can't do that. So I bring the 2 out front, and the derivative of e to the x, everybody is? God, say it like you want to be here, man.
Say it with your chest.
Yeah. Here is another function. This is different, okay? This is an e to the x. This is saying that I have some value x, and this is the derivative. Again, there it is because I told you that that's what it is. I probably, what I would do, and I don't think I might have a little cheat sheet, is I either would start making you a sheet of these shortcuts, I mean, even put, e to the x, the derivative is e to the x, because when you take a test, you lose your mind and you forget things, right? And just put these on there. I'll look and see if I have something, though. But in this case, I'm just telling you this derivative, so you're just taking the log. I was going to get you if that was you again. You're just taking the log times that value to the x power. We can't go through and prove this. I just have to say, there it is, use it, because we later come up with something that's called the chain rule. Again, some of you may know this already from high school, where you do some of these inside-out composite functions, basically. So for now, if you have an example like this, you just make it look like that. 3 to the x, the derivative, ln of my base. You can call it my base there. And then I just simply write that again, okay? I know that probably bothers some of you. It would bother me because why? We just don't have the tools yet until, and maybe the next chapter coming up. If I have, once again, something with a constant, do not think you can multiply that, okay? That would be, think about this. If that was 5 squared, you can't multiply 4 times 5 and get 20 and then square it, right? And so this is just, once again, actually pulling out front. And then I have this definition. Am I boring you? All right, and so I have my answer. And a lot of them, it's going to be just use them. These are the definitions for now. Here is another one, this e to the kt. We said the e to the x is e to the. In this case, if I find the derivative of e to the something times a variable, okay, so like we could still use x as 2x, then actually whatever this value is, I'm going to bring down. Okay, if some of you think about this, even though you say, well, I never had this in high school and I don't know what the chain rule is, basically what we're doing is we're taking e to the anything is e to the anything, and then we're taking the derivative of what's up top. And that's what you're going to find out what the chain rule says you have to do. But in this case, for memorization purposes, whatever that number is hooked to your variable, okay? All right, so the derivative of e to the 2t, I just bring that 2 down, and then e to the 2t. I can put some of these slides back up there when you're doing your group work. All right, so now for f of x equals ln of x, and you guys remember what the derivative is? 1 over x. So again, these are for, these brainiac kids, right? That your memorization people, not like the guy we're going to beat up in the parking lot, right, Rafiki?
We like to be called geniuses.
Geniuses. Oh, did I laugh out loud? I'm sorry. Okay. All right, so anyway, this is the definition. This is the beginning of this lecture. If you look at this, remember if I graph the derivative, and you should do these on all of this. Remember if my derivative's positive, I'm above, this might look better if it looked like that. I'm above the x-axis, so this is positive, but it's starting to get, my slope is getting less and less and less, is why I'm heading here, but it actually never goes flat.
Can't really see the graph.
Yeah. Hold on.
What?
I think I might be going blind.
I think you're going blind.
Is it?
Wow, that's weird.
Okay. Why don't you just draw it? Pass it over with the pen.
That would be like being a genius, thinking of that. Now, that's my true genius right there. Well, hopefully you knew what a logarithm looked like, right? So this is ln of x, and this is 1 over x. And actually, yeah, technically that. Okay, so now back to, now I got to say that all over again. Be interesting if it records this. So in other words, I have positive derivative. I'm above the x-axis. It's starting to even out and heading to 0, but it's actually never going flat. Okay. And again, we'll get into something later with this. This is something you see a lot with a population, and of course the other way with exponentials that turn into logs, and we end up with a carrying capacity, meaning that people keep having babies, right, in San Antonio, but eventually there ain't going to be no more room for you, so you got to move, right? Not looking in your direction that you have. All right, and so what in the world is that division sign there for? I don't know. All right, so if I do, for example, something like this, always look, I don't know what the division signs are, always look for pull out of this, which would be the 1/2. This is the same thing as 1/2. 1/2 is a constant. So all I'm taking is the derivative of this, which is, and thus you get your final answer. 3.1, and I don't know if you guys noticed, I made 3.1 homework due like last night or something. I don't know why. I just, I was in a bad mood. I don't know where I got that date from. It's not due until, I think, this weekend. Is it even due this weekend? I don't know. The 5th? Okay. And 3.2 as well?
Yes.
Okay. Yeah. So I just added 3.2. Yeah. So 3.1 and 3.2. I think most of you, and can you agree, can get through it pretty quickly? Because I know you've done 3.1.
I did 3.1
Okay.
and I had everything but that last question.
Okay. And I'll mention that on the last question in 3.1, what I would do is multiply. You have something, I don't know if you remember exactly what it was.
I have it on my phone. I can.
Like x. Well, what I would do is multiply, distribute this out, and anytime you have this, change it to that. Okay, and so then you have 2 over 2, so you have x to the 3 over 2. I'm sorry, you guys, way over there. That's what you get for sitting in the corner. And so now this is easier to take derivatives of, right? You bring that down, pass it around, and I'm out of the beer on the wall. And you bring that down, you pass it around, and you subtract 1. And so this is a lot easier to find the derivative of than just looking at that. Okay, so you had to kind of think of that. What was in the parentheses? This was square root of x, right?
Square root of x, parentheses, x plus 20.
Okay, so just a number, yeah. So the same type thing. And so just remember this on the last one. I don't think, especially after you get through today's, because you're going to do 3.1 group work, hopefully 3.2 if you can. I don't think you'll have much trouble with these questions, okay? And very likely you will have a quiz on Thursday. Why do we have a quiz on Thursday?
Because it's Thursday.
How long have y'all known me? What's important to me? The game! So that's why you will have a quiz on Thursday, because you need a reason to go to the football game. No, this Thursday. The game's this Friday, or Saturday. Saturday, yeah. 10-4, Saturday. All right, so here's an application. The population of Nevada in millions can be approximated with this function. Okay, most populations you're going to see are going to have these exponential, where t is years since the start of 2000. And I'm not going to pick on you, but I think of you right away with why are the numbers so huge? Anytime you deal with dates, always make your starting date 0. Doesn't matter that there's zeros on the end. This could be 2001. Let t equal 0 mean 2001. And it doesn't mean that your answers were wrong. It just meant she had to deal with a lot larger numbers because she's, good gosh, do you want to put that to the 2000 power? I don't. I think my calculator. All right. So at what rate was the population growing at the beginning of 2009? So since I'm asked for a rate, I want instantaneous rate of change, which is derivative. Okay, just means the same thing at this t. So, and this is where I said where they had all the different ways to write derivatives. You could write the same thing up here. What you're finding is p prime of 9. I wrote it like this because it helps me. And I saw some of you guys, what do you put on the top? What do you put on the bottom? It helps me to see, one, my units, okay? So my population over years, okay? So that's my time, my millions per year. And then it helps me here to know how I'm going to write out my derivative. So this is saying, what is the change in my population as time? So I just simply rewrite this, okay, so you can just see this is here. The variable that is on the bottom is the variable of interest. We do get in a little bit where you could have more than one variable here, and this is a variable I'm concentrating on, meaning anything else I would pull out front, okay? What I would do next is, this is being multiplied, I can bring that 2020 out front. Now I have this that is my definition here. Okay, so to find the derivative, I take ln of this base, and then I just rewrite that again. Okay, after you work, this is kind of a weird derivative, but after you work enough of these, you'll finally kind of get this down. And then, so I have, so now I plug in 9, okay, because I have all this in terms of a rate. And then I put that in my calculator, and I get an answer. Write it in a way that would make sense to me. This says it's in millions, but I could also write this as 98,220 people per year. Okay, so all of these I see it's good for you guys getting your calculators out. You should always check these. And a lot of the reason why is I see students not doing the LN. You didn't get that?
I got it. I got 98.22.
Yeah, I got that.
Okay, so from this stage right here, you got 98.22?
Yeah.
Okay, so I just wrote it wrong here. Thank you. I appreciate you checking that for me. Okay, so be sure that when you're putting these in your calculator, you know either to use the LOG or the LN in this case, and you're either breaking this down into one piece and then multiplying. What's nice now, hopefully you got, let me see if I can get rid of some of this junk. You have this piece here. The reason why we did this and we left the t alone, and this is very, very important, is because this gives me a function that now I can do it. I could say, well, what about 2010? Well, I just plug 10 in. What about 2011? I just plug 11 in. And that's what we want to get to. We don't want to always end up with a number here. We want to end up with my step before with a function that I can plug in. All right, this is kind of for those of you, if you end up with the Breaking Bad project, it's something like this, where you end up with a certain drug in your system, okay? And this is the concentration, at T hours it was administered, the concentration of a drug in the body is this. These you have to be careful when you're asked, because this says, what is the concentration at 4? What do?
You just put it 4.
Exactly. Most students, we're in calculus class, I bet we have to find a derivative. Always look for the word rate, okay? This up here, if you go back and read, it says this is the concentration, okay, after T hours. So the first step, that's all we're going to do. We're going to just simply plug that in. You guys with your calculators, check me on this one too. And so all I'm doing is I'm plugging in for my time the 4, so e to the negative 0.14 times 4, and then multiplying that by 27. And here again, always look for your units. It's going to get where quizzes test things like that. You know, I might do a little -1 because this class is way more important with units, okay? Because you certainly don't want to administer something wrong just because you have the wrong units. Did you get that? Okay, thank you. No.
Yes.
Oh. All right, and so then the rate means you need to find the derivative. Notice I kind of didn't write this all out. I know you hate it when teachers skip steps. I brought that 27 out front. This is my e to the kt, where I bring what's up here down, and I leave that alone. Okay, so that's all I've done here. This is that little definition of my e to the kt. My derivative is the k and then e to the kt. All right, all I have to do here is plug in my 4 again, and this gives me my rate, which I'm hoping you guys are starting to think about things in here and say, well, that makes sense because we hope it would be negative, that it's actually leaving the body. All right, so, in fact, I think this is just like it may be exactly your group work problem. Okay, so, sure. What'd she say? Somebody said, what'd she say? It probably wasn't important. Shh. And log.